Alright, let me try something a little different for this video. I'm trying off my phone to see if that gives y'all a clear picture where y'all can see everything a little better. Alright, so we're going to pick back up with section 2.1. Last time, here's what we looked at. We looked at, let's suppose I have some kind of curve. Y is equal to f of x here. And then I pick some point, like let's say this is, I don't know, maybe over here, I'll pick it. Let's say that this is the point x subscript to 0. Okay, so right here I have an order pair x subscript to 0, f of x subscript to 0. Now, what were we looking at last time? We were looking at the tangent line and the slope of the tangent line. So remember, the tangent line is the line that touches the curve at that point right there, right? So we said m tan, the slope of the tangent line, is equal to the limit as h approaches 0 of f at x naught plus h minus f at x naught all over h. But we looked at something else. We looked at f at x naught plus h minus f of x naught all over h without the limit on the front of it, without that part on the front of it. What did we say that was? We said that, okay, what if we move h units over here? H units from that point right there, we call that x naught plus h. Then that gives us a point like, let's say, right here. And then I have the slope of my secant line. So what is this difference quotient without the limit? That's the slope of the secant line, is what that is. So slope of the secant line is difference quotient. Slope of the tangent line is difference quotient with the limit. All right. Now today what we're going to get into is velocity. We're going to look at average velocity. We're going to look at instantaneous velocity. Now we're just looking at rectilinear motion in this class. We're just looking at motion that goes straight up, straight down, straight left, or straight right, and it could go back and forth. Maybe it goes like this at a diagonal, but either way, it goes along a straight line. It doesn't do like this, a curve or anything, okay? All right, so we're looking at rectilinear motion, and your book talks about average velocity, and it talks about instantaneous velocity. It talks about average velocity of a particle over a time interval. So it says average velocity of a particle over the time interval. I'm just going to put it over t subscript to 0 to t subscript to 0 plus h. So maybe that's like from 2 seconds to 3 seconds. Maybe that's 5 minutes to 35 minutes, okay? Just over some time interval like that. And it defines the average velocity. It denotes it VAVE. And it defines it as change in position over change in time. And I'm using delta for change. And it says that is equal to f at t naught plus h minus f at t naught all over h. So basically they're saying the average velocity over the time interval is the difference quotient. So the same thing we have for the slope of the secant line, but we're using t's instead of x's, but that really doesn't matter. It's whatever you choose your variable to be. Then it talks about your instantaneous velocity at time t naught. At time t naught. Instantaneous velocity at time t naught. And here's what it talks about for the instantaneous velocity. It calls it V inst is equal to the limit as h approaches 0 of f at t naught plus h minus f at t naught all over h. All right, so what's it saying about the instantaneous velocity? It's saying the instantaneous velocity is your difference quotient with the limit. It's saying your average velocity is just the difference quotient. So my instantaneous velocity is like the slope of the tangent line, and my average velocity is like the slope of the what? secant line. If I'm trying to put this all together, group it in my brain to where it makes it easier for me to memorize. All right, so let's look at the example we have from our notes. Now, this is a long set of directions, I guess you can say. Not really directions, but description of the problem where it talks about a ball is thrown into the air with a velocity of 40 feet per second. Its height in feet t seconds later is given by our function f of t is equal to 40t minus 16t squared. Now, I'm not going to write all that down, okay? You got it in your notes. Look at your notes. I am going to jot a few things down here, though. Okay, so it's saying its height in feet t seconds later. Height in feet is given by this function here. F of t is equal to 40t minus 16t squared. And t is the time in seconds. Time in seconds. Okay, part A, they want us to find the average velocity. I'm going to abbreviate here. Find the average velocity for the time period. Beginning when t is equal to 2. We're going to put starting when t naught is equal to 2 and lasting 0.5 seconds. And lasting 0.5 seconds. All right, so what do they want me to find here? They want me to find the average velocity from t subscript of 0 to 2, lasting 0.5 seconds. So if I think about my interval, that'll start at 2 seconds, and if it lasts 0.5 seconds, that means it goes to 2.5 seconds, right? Now, we just learned before I erase the board that the average velocity is equal to what? The difference quotient. F at t naught plus h minus f at t naught all over h. And if you prefer to use the x naughts here, that's fine. Well, let's see. If I fill in now, what does this tell me? Let me come over this way so give myself some more room. What does this tell me? F at t naught plus h tells me here and here I'm going to sub in t naught plus h. So I have 40, but instead of t right here, I'm going to put in t naught plus h minus 16 times t naught plus h squared. So that takes care of this part, right? Minus f evaluated at t naught. So minus this stuff evaluated at t naught. Let's see, that gives me 40 t naught minus 16 t naught squared all over h. All right, let's see. Let's distribute this 40. So we get 40 t naught plus 40 h minus 16. Now, what's the quick way to square a binomial again? Square the first term. So that gives me t naught squared. Multiply these two, h t naught, and then double that. So it's 2h t naught. And square your last term, plus h squared. Now distribute your negative through here. So you get negative 40 t naught plus 16 t naught squared all over h. All right, right away here, I see 40 t naught. I see negative 40 t naught. I can zero that out, give me less to right. So what do we have left? 40h. 40h. Distribute your negative 16 through here and you get negative 16 t naught squared minus 32h t naught minus 16h squared. Then at the end, we have plus 16 t naught squared. That's all over h. All right, now, negative 16 t naught squared, positive 16 t naught squared, going to zero each other out. Let's see what else we got here. Well, I can't zero out any of these other ones, right? But notice how each one of these terms left up here has an h in it, and we have h at the bottom. So in other words, I could think of this as 40h over h minus 32h t naught over h in this term over h. So in other words, I could divide each one of these terms by h. And what does that give me? That gives me 40 minus 32 t naught minus 16h to the first, right? Now, I just need to fill in for t naught and for h. Well, they tell me what t naught is. They tell me t naught is 2. So 2 is going to go right there. How about h? H is the length of the interval, right? How long is this interval if I go from 2 to 2.5? 0.5, right? So my h value is going to be 0.5 that I sub in there. So this is going to be 40 minus 32. We said t naught was what? 2 minus 16 times h. What did we just say h was? 0.5. So I get 40 minus 64 minus 8. So what's 40 minus 64? Negative 24 minus 8. What's negative 24 minus 8? Negative 32. Now, what did I just find? Average velocity. So what's my units? Well, let's see. That was the outputs that were changing up top, right? And basically it was the inputs changing down below. So what's the units for my output? What is F of t measured in? Feet over, how about my input? Second. So the unit is negative 32 feet per second. So the average velocity for 2 to 2.5 seconds is negative 32 feet per second. Let's look at part B. Part B of this example. Let me see. I'm going to have to erase something here. Okay, if we look at part B, it wants us to find the instantaneous velocity. Find instantaneous velocity when t naught is equal to 2. Now, how do I find an instantaneous velocity? Let's say v-inst is equal to the limit as h approaches 0 of f at t naught plus h minus f at t naught all over h. Look at this part right here, this difference quotient. That's the same as this part right here. Already calculated this difference quotient, right? And before I subbed any numbers in over here, what did I get for that difference quotient? I got that part right there, right? So I don't need to do the work twice. What I could do is I could say, okay, this is the limit as h approaches 0. But now, instead of writing this difference quotient, I already simplified that to 40 minus 32 t naught minus 16h. So I'm going to say this part turns into 40 minus 32 t naught minus 16h. Well, let's see. Can I evaluate this limit? Yeah, I can sub in 0 for h and I'm okay. So let's do so, because that's just really a polynomial. 40 minus 32 t naught minus 16, h is 0 here. So that gives me 40 minus 32 t naught. But what is t naught? What is t subscript to 0 here? 2. So I'm going to put 40 minus 32 times 2. Well, what does that give me? 40 minus 64. What is 40 minus 64? Negative 24. It Again, I'm looking at a velocity, in particular an instantaneous velocity, but my units are going to be feet per second.